My name is Ilya Benish, and I'm a building analyst for the Cold Climate Housing Research Center here in Fairbanks, Alaska, Climate Zone 8. And in this video, we've got a situation that we've finally been able to document, and the industry refers to this as a thermal bypass, and loosely defined, a thermal bypass is anywhere in our building thermal envelope where heat flows through or around insulation, essentially rendering it less effective. And one of the most common forms of a thermal bypass is air leakage driven. And so this means we've got heat losses due to air leakage. And in cold climates, often those heat losses due to air leakage also result in undesirable moisture transport into wall assemblies, leading to all kinds of problems with mold and rot. Now, what we've got here in particular is a 1970s home, and you can see the garage is attached to the house, and it's a split level. And the problem area is where the garage roof intersects the house wall. And this isn't exactly how this problem occurs in every situation. It's really anytime you have one heated structure attached to another and how you transition your insulation and your air barrier through that wall assembly. In this video, this is the first of 3 examples we're going to show that exhibit this air leakage driven thermal bypass problem. The other 2 homes will be using an infrared camera and a smoke test to highlight the same issue. Although it looks different from the outside, it's very much the same on the inside. In this first case study, the contractor has gutted all of the inside of this home, so we'll be able to go in and actually look at this wall assembly, talk about our thermal bypass, and how to repair it. I'm now standing inside the living room of the house, and we're right here at our problem area. This is our air leakage related thermal bypass. This wall has obviously been gutted down to the studs. I've got a clean view here into the garage. I can see and reach into the garage attic. It's woefully under insulated, by the way. This looks like our 19 fiberglass bats. What's problematic, though, is how this wall was air sealed. And unfortunately, this is really common in split level older homes. And even nowadays, we're seeing this problem continue. And what's going on in this case is the vapor retarder from the garage ceiling went and sealed down here to the bottom plate. It was just stapled on because this predates the sealing methods we use nowadays. But in addition, on the front side, there was a craft-faced fiberglass bat insulation, but there's no transition for our thermal and our pressure boundaries to carry through this wall. And so I don't think you could ever air seal this wall well enough on both sides not to prevent each one of these studways from being a chimney. You have to install blocking, and that's going to be our next step. But when I look up here, I see evidence of years of water staining. I don't see a lot of rot, but I can see that indoor air leakage has been traveling up into here and condensing. I also see water staining underside of the garage sheathing. And you know, I think this house got lucky. It's an older home. It's obviously an energy pig with lots of air leakage. And in this case, that means this place dried out pretty well. I don't see that as an excuse that we should build leakier homes. I see it more that we have to address these thermal bypass problems and continue our thermal and pressure boundaries right through where we have continuity between whatever heated structure is attached on one side to the heated structure on the other side. So let's get started. Right here, I'm going to start installing my blocking, and I chose this spot here because we also have a plane change in our thermal and pressure boundaries where we transition from garage roof to garage wall, and on the other side, the house wall. And I got lucky here. I still have a little bit of vapor retarder showing from the garage ceiling. So before I permanently install my blocking, I'm going to run a bead of acoustical sealant right along here on the vapor retarder, and then I'm going to install my blocking so that the top of the blocking in this case is flush with the bottom of the truss. and then I should get a pretty good seal right here. I'm doing this because I can, because I'm trying to do the best job possible. In addition, there's a whole other issue I haven't talked about because we're focused on thermal bypasses, but this is a garage. And so there's health and safety and fire codes that relate to separating the garage from the living space. You know, we don't want carbon monoxide getting into here either, and we want fire blocking. So our air sealing blocking is serving a lot of other purposes in this case. I look at this old wall and I look at the bottom plate, and as it was built, it's been leaking air for years and moisture's been depositing on this plate. It's still sound, but the nails are rusty, and there's just a lot of evidence of decades of air leakage. Moving ahead, as I transition here, I've got a hole pre-drilled for a wire that's going to go through here and get caulked, but I'm doing the same thing. I'm installing my transition blocking here so that I'm just at the edge here of the garage wall, and this will all get caulked. I'm just going to catch it here and here. This will all get caulked inside here, followed by spray foam. So we've got a belt and suspenders approach to being able to air seal this entire transition. And then on this side, the garage vapor retarder can seal to our blocking. And on this side, the house vapor retarder can also seal and transition our thermal and pressure boundaries all the way across here. So we should have a really robust transition from one to the other. I've now installed 2 blocks in the row of blocking that needs to be installed here to transition our garage ceiling pressure boundary to the pressure boundary of our intersecting house wall. One thing I want to mention is a correction. I did use initially Tremco acoustical sealant because that's what I would typically use when bonding poly to wood. In this case, I don't think it's absolutely necessary, and it can get messy. Instead, I would probably use a high quality adhesive caulking like this Carlisle Barabond. It's got reasonable adhesion to poly, it's gap filling, it doesn't shrink, and it bonds like crazy to wood. So I think it's a product like this would be an excellent all-around sealant for sealing this transition. As I mentioned earlier, a spray foam contractor is going to come onto this job site and then fill each one of these bays and seal against these blocks, as well as seal inside this area and all the way along. The spray foam will also reach the back sides of these studs and encapsulate everything. So that will add additional insulation, and there will be more insulation blown into the attic. One other thing I'd like to mention is I don't feel like you can leave the caulking out if you're going to be filling this bay with spray foam. I think you're going to get better long-term assurance that this area will remain airtight if you caulk it first, even if you're filling all of this with spray foam. I think it's just a more durable seal. Other than that, I think once this is all blocked and sealed, we will have successfully addressed our thermal bypass problem on this project. It's a warm day. It's not quite a spring day, but we're getting close. And we're actually out here in Fairbanks looking at an older home. It's probably the most common style of home that we have, built during the pipeline era in the late 70s, early 80s. And we found a very common situation, but also very interesting. And we're going to take a look at that with the infrared camera and then describe a little bit what we're seeing.
We're seeing increased heat flow out of one wall section above the attic, the garage attic space. We're seeing several hot spots at the top of the wall. Besides the 2x6 24-inch on-center framing, we see an increased heat flow out of that wall section. And it occurs because we don't have exterior sheathing inside that attic space. You have exposed fiberglass, increased convection through the insulation, and that heat just starts generating and increasing up through the wall and accumulating at the top of the wall. You add in plumbing walls, you add the tub surrounds that are exposed on that attic space, and you get a lot more increase in heat loss through that wall section.
Well, it's lighting up like a candle right above this garage roof.
Several different spots, and they line up with walls inside as well.
So when we walk up to this, you know, it looks pretty normal here. As soon as we get to where this garage roof starts over heated space, we get the hot spots. And so this garage truss, the last truss, was nailed to the house wall, but it's not air sealed very well. So indoor air is traveling up in this wall assembly and getting up into that house attic. And that's a common bypass that we see in these older homes. We are now at a home in Fairbanks in May, and we are going to conduct a series of diagnostic tests on this home because it has suffered from one of the classic problems that occurs when you take an existing home and you add an addition onto it. And that's what happened here. A two-story addition was added onto the existing home, and for years afterwards, in the wall and the roof, between the two structures, moisture problems were occurring in the wintertime, and there's been at least 2 attempts, expensive attempts, to try to address this air leakage. And so far, all of these attempts have failed, and there have continued to be moisture problems due to air leakage in the roof and the common wall between the two homes. And today we have Emmett Leffel from ATI Services with us, and he's going to conduct a series of diagnostic tests to help us identify once and for all the source of the air leakage.
We're going to actually measure the air leakage for the entire home, and then we're going to depressurize and map the air leakage coming into the home with thermal imaging, and then we're going to pressurize the home and map the air leakage going out of the home with fog. And so you'll be able to visibly see where the air leakage is coming out of the home, and we'll be able to map the air leakage coming in with the thermal imaging.
We are now in the master bedroom. I'm standing next to the master bedroom closet, and this is where the recurring problem has been taking place every winter for years. And the issue we suspect is the common wall where the new house wall was attached to the old house wall, and the moisture has been coming down through the closet ceiling. And we're going to conduct a series of tests to determine if that's truly the case, and we do have an air leakage between the new structure and the old structure.
All right, so we have the blower door test operating right now. We're depressurizing the home. We've measured the air leakage for the entire home, and we're at 3 air changes per hour. We're just over, we're at a 1,600 plus square foot home. And so it's an average size home. And we meet the IECC requirements for air tightness for this climate zone. There's different ways to find air leakage. We can feel it with our hands. We can also look at it with a thermal imaging camera if you have it. And we've identified air leakage at some vapor barrier joints at both walls where it's not sealed at the wall ceiling joints. There's some air leakage at the wall floor joint. And we can also feel, like I said, oftentimes all you need is your fingertips to find air leakage. When you're depressurizing a home, we're depressurizing to 25 pascals right now, and I can feel cold air coming into this corner joint between the vapor barrier and the framing. We just set up the fogging equipment here. It's a commercial fogging system. Here we're going to be testing and mapping out the air leakage pathways through a building envelope, and you can start to see it's ready to heat up now. We're going to turn this on and fill this space with fog. We've got the blower door system set up and pressurizing the home so that we'll be pushing air through the wall system, and with that all the fog, and we'll be able to map that through at the exterior of the home. We've got the home pressurized, and we're filling the zone with fog, and it's quite obvious where the air leakage is coming out of the home and where the air leakage pathways are.
We are have the fog machine in the master bedroom, right on the other side of this wall, and where that smoke is coming out of the roof is the master bedroom closet, and that's the area we had suspicions we had air leakage, and this is validating that we were correct. And now the next step is going to be to open up this area and investigate those leaks further. Now we're back inside after running the fog machine, and we've removed the plastic from the closet ceiling. And this is one of the pathways that we suspected, air leakage pathways, and it's between the two walls, the wall of the addition and the old wall of the house. And last January, when the water problems first started, I marked these spots when we looked inside here, and I could reach over this rafter and the insulation was saturated. Even today, I can reach over this wall, over this rafter, and get into the space between the two walls, and that insulation is still wet. So all indications are pointing to an air leakage problem that needs to be addressed here. And unfortunately, it means removing at least all the sheathing off of this rafter bay, as well as probably the sheathing on the wall of the addition. We're now looking further up this rafter bay beyond the closet, and this is the rafter bay right next to our common wall. And we've already pulled this insulation down to get a look, but this insulation was completely blocking this vent space. And remember, when I reached over the rafter, that insulation there was still wet from condensation last winter. If this vent space wasn't blocked by insulation and were working properly, you would have a drying path. And we can see here from the dry rot fungus that has started on several of these purlins and the dark staining that this has been going on for a while. So the other thing that needs to happen, in addition to air sealing all the leaks in the common wall, is the builders need to make sure that at least a 1.5 inch airspace continuous from soffit to ridge exists. So if any moisture does get into this roof system in the winter, you've got a proper drying path. It's now August, 3 months later, and we were able to time the opening up of this roof so we could conduct another smoke test. At this point, the roof is open and it's ready for the smoke test, and we're getting our first look at it. We have removed the fiberglass insulation that was in this first rafter bay here, and sure enough, just like we saw from below when we were looking up through the closet opening is right below me, but when we were looking up through the closet into the roof, we saw that the insulation was plugging up the rafter bay. Every single space along here was plugged by fiberglass, so this roof just didn't have a good way to evacuate moisture and condensing and dry out. What's also really interesting is we have another manifestation of that air leakage driven thermal bypass, where we have a wall that changes from an interior wall to an exterior wall. You can see this right here. Here's the old house roof. Here's the new house bathroom wall. The bathroom is against an exterior wall, and the plates run all the way along here. And so we know historically that there's been condensing events in here, and this foam here is one of the attempts that was made to try to air seal this bathroom wall to keep that moisture and air leakage out of this rafter bay. What I can see is that not just were these bays sprayed, but there's also been 2 inches of continuous foam sprayed up the entire length of this rafter bay in an attempt to air seal it. The smoke test will tell us if we continue to have air leakage in any of these bays, which we suspect. Remember, I was able to reach over this bay in the wintertime and grab wet fiberglass. We've taken the fiberglass that was in here out, but that was a strong indicator that there's still an air leak bringing water vapor from inside into this bay. So our next step is to conduct that smoke test and see what we can learn. Well, we learned a lot from the smoke test, and I think I can break it down into 4 different distinct problem areas, starting at the bottom of the roof. Right here in this first bay, remember the bathroom is here on the other side and the closet is right below me. there was spray foam applied here to fill this bay, but the smoke test showed us that there's a $half sized hole right here in the corner. I can stick 2 fingers in it, and we know that that goes straight down into the closet wall. So there's a direct air leakage pathway from inside into this bay. I'm kind of surprised that this entire bay wasn't just filled and sealed with spray foam. That would have been the ideal solution instead of placing the fiberglass in here. Our second problem starts here at the bottom of the roof, but it extends all the way up to the peak, and that is when the addition wall, the new wall, was butted up against the house wall, suddenly the old house T111 siding became a conduit for indoor air to leak up into this rafter bay here and into this wall. All the way along here, I can see the old siding hasn't been sealed. There's some foam overspray here, but that's incidental. Not only is the sheathing joint where it meets the rafter an air leakage spot, but all the vertical channels in the T111 are also pathways for air leakage. So these have to be sealed and addressed as well. Our third problem is more complex. And the issue we found is the area above the closet ceiling that we had to cut away to inspect the roof and to let the moisture out. We saw massive amounts of smoke coming out of this area during the smoke test. In fact, it was so much smoke, we had to stop the test, clear the smoke out, and then we could see what the problem was. And it turns out that the poly itself underneath this foam wasn't sealed. So we have an overlap right here that wasn't sealed. So we've taped that and sealed it up. The issue with some of this is that when you apply spray foam over poly, the spray foam doesn't bond to the poly. And I have had several professional spray foam installers tell me if you apply spray foam at, say, 2 inches thick, like was done here over poly, you run a risk of that foam not curing properly and possibly even separating from the poly. And that's what I'm seeing here. I have a gap between the foam and the poly that's as thick as my finger. And what that means is any air leakage through poorly sealed poly will travel around under here until it reaches a hole in the foam. And that's our fourth problem. Because this foam, we theorized, didn't cure properly being applied over poly, it had a series of small holes. Actually, some of them were about the size of my pinky. And that's where the smoke came out of. And I think we probably had 8 areas like that that we now have to seal, because remember, the foam isn't bonded to the poly. Indoor air is migrating between the foam and the poly until it finds a hole. Our fixes to air seal all the holes we found during the smoke test, those are pretty straightforward with one exception. To start with, we're going to patch this large hole we cut into the foam with foam board and more spray foam. But as far as all of the actual air leakage points themselves, most of them we can fix by injecting more minimal expanding foam into the holes or places where there's channels on the backside in these stud bays that we could feel and see were open and the smoke came out. We can inject foam into there. The one tricky area is going to be sealing this continuous gap that runs between the old siding and the new wall. That's a continuous airspace up this rafter bay. And I realize the tendency is just to want to seal right here at the top. The problem with that is our primary pressure boundary, the spot that separates our indoor air from our outdoor air, is down below here at the bottom of our foam where our polyethylene sheeting is. So realistically, we need to start our air seal, I feel, down here at the bottom of the rafter. And in order to do this, we're going to drill a series of 3/8 inch holes every 4 to 6 inches and inject minimal expanding foam here. The theory is that foam will expand and air seal right there at the pressure boundary. If we don't do that and we just air seal here along the top, we've still got this airspace here. It may be a dead airspace, but it still communicates, and indoor air can still get in there and condense because it will be cold. That, in theory, could lead to a future problem with dry rot. So I think in this case, an extra couple hours trying to air seal down at the bottom is well worthwhile. In concluding this video, I'd like to make one specific point, one takeaway message here, and that is to be able to identify these types of thermal bypasses and the different ways they can occur. And we've tried to present that with 3 different examples. The point here is you have to catch these problems at the start. With new construction, it's easier to deal with, but you have to take the time to identify your thermal and pressure boundaries, and you have to figure out where that air sealing needs to occur. During remodels, it's more trouble, but you will have to open up the wall and you will have to identify where's your pressure boundary and where does your blocking need to go. There's no way around it. If you think you can rely on air sealing, it will never work, and you will end up with a case like this where we were the 3rd attempt at fixing this roof. It's far better to address this, to identify it and address it at the start. As always, we welcome your questions and comments, and we'll provide more information in the video description.